I'll just do a we'll build on this field and we'll find equations to solve the field problems. Right. So do you have any questions regarding uniform field? You can let me know. So just a quick reminder, it's a region in which uniform field, it's a region in which a charge will experience a constant force. So imagine you release a charge here, right? Regardless of where the charge is in this field, the force will always be the same. That's called a uniform field, right? And to generate a uniform field, you need to have two parallel plates, and there must be a potential difference created that will create a field here. Okay, so that's what a uniform electric field looks like. Question, number of lines. Number of lines actually mean something. What does it mean? The number of lines. Strength of the field, right? So if I had double the number of lines here, visually, you'd know that this field is twice strong as the previous one. Okay, so that's that part of it. Also, why is the force constant, right? So yeah, why is the force constant? The reason is, it's here, I've written it down here as well. So the reason the force is constant is because when your charged particle, let's say it's a positive particle, and it's here, it is experiencing repulsion from here. So blue arrow tells her repulsion. And it's also experiencing what from the bottom? Attraction. So these two together will give you the resultant force, right? But as you start to move further away, the rate at which your attraction increases is the same rate at which your repulsion decreases. So overall, you'll find that attraction is increasing, repulsion is decreasing. So your overall force remains constant. And that's the reason why this is a uniform electric field. Okay. So also just keep in mind that the force will always act like that, downwards. Okay. Parallel to the field. So even if your particle is going this way, the force will be what? Downwards. Okay. So yeah, that's what your uniform electric field is. Okay. It means you have just crossed the midpoint of the plane. That's it. Okay. Because it's linear, so it must be the midpoint. Right, so let's move on. We'll try to derive equations. So go to page 97. Page 97. Okay, so what are the equations of electric field? So listen carefully. A topic target table. This has a lot of value in your syllabus because you're definitely going to get a question from here. Okay, and question uniform field to কম আসার কথা, but তাও important. And I don't know if you know this. Uniform field was AS chapter. You'd find this in your AS, past paper plenty chilo. Now they brought it to A2, okay? So obviously, if they bring it to A2, they'll also increase the complexity of your questions, right? So we'll see some complex questions in your A2. So anyways, for practice, we'll be doing AS questions because A2 te ekhono ekta question asche so far. Right, so this is your positive plate, and this is your negative plate. Can you remind me what was the formula for electric field strength? E, electric field strength, is equal to what? Force by charge, right? So it's the amount of force exerted per coulomb charge, F by Q. Very important equation. Now, if you see here that there are two parallel plates, and this is negative, and you have a charge here, and it experiences a force, and that force is the electrostatic force. Let's call it Fe. And the distance between the plates is given by D. And it's a potential difference. Okay, so the PD between the two plates is V. These are the quantities that we know so far. This one's the mass is M. So right now, what we want to do right now here is to find the energy transfer going on here. So can you tell me, if I take a charge, right, and I move it against the field, what does it mean by move it against the field? So the charge that I have here is positively charged, okay? And I'm taking it against the field. What does that mean? So this is negative, this is positive. Which way do you think this charge is naturally supposed to go? Downwards, right? So when something goes naturally in the path of its motion, it loses energy. And we have seen this somewhere, gravitational field. So in gravitational field, when you let the mass fall and it does its thing naturally, it'll lose GP and gain what? Ke. But if you take it against the field, what does it do? Gain energy, gain potential energy, right? So in this particular scenario, what's happening is your particle has been raised from here to there. So you have gone against the field, which means the particle at this particular location is now storing something. What is it? It's called the electrical potential energy. Okay, electrical potential energy. And as you let go of it, what will happen is that the electrical potential energy will be converted to some other form of energy. Do you know what would that be? Yes, because it's going to move, it's going to accelerate, so K to convert of it. So by the time it reaches the bottom, this charge here, right? By the time it reaches the bottom, it will have converted all the EPE to what form of energy here? Kinetic energy. Okay, so it solely has kinetic energy at the bottom. Are you with me so far? Acha. Now we'll take a different path here though. Do you see that there's a force being exerted on this particle and the force is constant? And do you see that it is covering what as it falls? Distance. Do you know of anything that may happen if there's a constant force exerted over a particular distance? Work done. Okay, so the thing is, there's work being done on this thing. So I can form an equation here. What equation can I form? The work done on the charge, must be equal to what? The electrical potential energy stored, because that is what the work has been converted into, right? Electrical potential energy. Now, can you tell me what should the formula for work done be here? Yep, the force, electrostatic force into what traveled here? Distance traveled should be equal to the electrical potential energy. This you should know. It's a charge which is Q, by the way. Does anyone know what's the formula for electrical potential energy? It was there in your AS, it was there in your O levels. Okay, I'll rephrase it. Can you tell me what's the formula for electrical energy? Yes, VIT is 1, but we don't have I, we don't have T. So what's the original formula for electrical energy from your O levels? Acha, online a couple of you said the answer, that's correct. Yes, it's QV. E equals to QV, V equals to E by Q. Remember the definition of voltage? It was in your AS. What's the definition of voltage? The amount of energy transferred per Coulomb charge, right? So V equals to electrical energy by charge, right? So electrical energy would do what? QV. It's a very important equation. It's something that can make a big difference in your age. Okay, so just don't forget it. Electrical work done is QV. And if I rearrange this thing, see what happens. So I'm going to rearrange Krita. I can write this as F by, like if I cross multiply it, right? What should it be? F by Q equals to V by D. Does anything here ring a bell? Correct, very good. So this thing that you're seeing here, F by Q, that's your electric field strength. And therefore, we have a new equation for electric field strength. Electric field strength is equal to V by D. And this will be the go-to equation for this topic. A chapter, almost every question that you start will start with this equation, E equals to V by D. But there's a catch. What's the catch here? This is only applicable for a uniform field. You can't use this for a non-uniform field. Okay. Also, the other catch, it's a trap that they set, is what is D here? Is D the distance the charge has moved, or is D the difference in distance between the plates? What is D here? Yes. So what they'll do is they'll tell that there's a charge somewhere here and it's going somewhere there, and they'll give you two distances in your exam. They'll provide you with this X, and they'll also provide you with D, right? Which one would you always use? D. You always use the distance between the plates. It doesn't matter where your charge is, because the field is due to what? The plate position, not the charge position. You get my point? So if this room was like an electric field, right? The ceiling would be a positive terminal, the base would be a negative terminal. The force that the charge experiences is because of what? The separation of the ceiling. So that's when I want to find the strength, do I take where my charge is, or do I find the distance between the plates? Distance between the plates, right? So I'm going to make it, but I hope you understood this. So this is your electric field strength. Electric field strength. So that formula that I taught you the other day, F by Q, right? You'll find that eventually it's not that useful, because for every scenario we have dedicated equations. like non-uniformity, there's an equation as well, okay? KQ by D squared. Anyways, this V here is what? So it's not voltage, that would be a wrong answer. It's potential difference, okay? So it's always potential difference. The term voltage is very rarely used anymore because it's an umbrella term. It's either potential difference and what's the other counterpart? EMF, okay? It's one or the other, it can't be voltage. And D is the separation of the plates. Separation of plates. Right, so that's the equation, and we'll be using the equation to solve the questions of uniform field, okay? Yeah. So what's happening here is that your charge, let's bring it back again. Have a electrical potential energy, right? So imagine I take this remote here and store it here. So what energy does it store? Gravitational potential energy, right? And if I let go of it, the GP would be lost because there'll be work done on it. What's the work done here? Yes, and that is because of the force, which is weight into the distance it falls. So if you remember in your A's, there was a derivation for GP, where work done is mg into d, so mgh. There was an equation like that, okay? So this is basically the reverse of that. So if you let go of it, it loses the potential energy and it turns itself into the work done, which eventually turns into what energy at the end? Kinetic energy, because whenever you do work on a system, it gets transferred to some other form. Right, so this is the derivation. Very important to note that the distance is the separation of the plates and not the position of the charge. তখন হচ্ছে যে নতুন পজিশনটা নতুন প্লেট সেপারেশনটা ইউজ করতে হবে মানে এখানে ডিটা হচ্ছে the separation of the plates, right? তো এখন আমরা যদি প্লেটগুলোকে কাছে নিয়ে আসি তাহলে কিন্তু ফোর্স আর সেম থাকবে না, ফোর্স কি বাড়বে না কমবে? সো নতুন করে ইকুয়েশন ডিরাইভ করতে হবে, নতুন ফোর্স চলে আসবে। Done? So what are the two ways in which you can increase the strength of this region? You can increase the what between the plates, potential difference, or you can bring the plates what? Close to each other. And we saw that in the other example the other day, if you remember that the plates were like this. So this place had a stronger field and it got weaker as we went out, right? And the stronger field there was because the plates were very close. This is the same. That's the mass. Field strength and separation of plates. So you'll get a potential difference, but you wouldn't know what the values are. So you'll just know that the difference in them is 500. So it could be 600, 100. It could be 300 minus 200. So, you can't, right? What does X represent? X, X ছিল হচ্ছে location of the charge. And the location of the charge doesn't really have an impact on our equation. Okay, a couple of questions before I move on. So this is it. V equals to V by D, okay? But strictly, this is only applicable for what? Yeah, it can do more because only use for and it's a mistake. Only applicable for a uniform field. Okay, so let's try a question. Basic just to make you know how to use the equation. So example. So you have these two parallel plates here. A voltage provide kora. This one is connected to a plus 4,000 volts. This one is connected to a minus 2,000 volts. And you have a charge here that's positive 1.6 into 10 to the power minus 19 coulomb charge. Okay. And this is a proton. So the mass of a proton, what was the mass of a proton? Very good. Yes. 1.67 into 10 to the power minus 27 kilogram. You're not supposed to memorize it, but if you don't have it memorized, it means that you're not studying enough. So anyways, so the separation of the plates here is 20 centimeters. And yes, what do you need to find? The acceleration. Find the acceleration when the particle travels between the plates. Right. So Cora, it's super easy. It's just I just want you to be familiar with the equation. Okay, it's like a prerequisite to something else. Right. So find the acceleration when the particle travels between the plates. What do you get as an answer? 2.87 into 10 to the power 12. V by D. A uniform electric field, so V by D. Two 2.87 into 10 to the power 12. So how do you find acceleration? So first of all, for acceleration, what do you need to know about the particle? The force. F equals to ma, right? How can I find the force? So I know that E equals to what here? V by D. But we also know that E is equal to what? F by Q, correct? So F by Q is equal to what? V by D. A relationship use করতে হবে তোমাদের F টা বের করতে হবে, Q is the charge, which is 1.6 into 10 to the power minus 19, equals to, what's the potential difference between the plates? 6,000. You have to take the sign into account, okay? So it should be 4,000 minus 2,000 divided by, what's the separation of the plates here? 20. You have to convert that into meters, obviously. So this will give you the force, right? But we can take one step further here. We know F equals to what? MA, right? So I can just put my mass here as well, which is 1.67 into 10 to the power minus 27 times A. So this equation, or this will directly give your answer, okay? So it's going to be 2.87 into 10 to the power 12 meter per second square. Clear? This would be like a start to a question, or a uniform field issue that they'll ask you acceleration, and then it can become a projectile question. It could become like mechanics question. Okay, one more example. This one is from the past paper. So দেখো পারো নাকি? এটা কি ক্লিয়ার সবার? কোনো কোয়েশ্চেন থাকলে বলো। 3 into 10 to the power 12. তুমি কি 1.6 নিছো এখানে নাকি 1.67? 1.6 নিলে 3. Right, so question. Right, a charged particle of mass 2 micrograms is held stationary in a field shown. So you have a field provided here, and there's a charged particle here. This charged particle is held stationary. Why is that unnatural? Should it stay stationary or it's supposed to move? Yeah, what is supposed to make it move? No. Let's say there's no field out there. Would something just stay stationary? Yeah, so the weight, right? So because of the weight, the particle is supposed to go which way? Downwards. But it isn't going downwards. So that means the electric field must have to apply a what force? Equal and opposite. So that balances, right? This is a very famous experiment. It's called the Millikan oil drop experiment. This is the experiment that helped us find the charges in electron. So Kikore, they release a charge in a vacuum, and the charge starts falling. And then you keep tweaking around the electric field, you'll find the charge starts to move around, and then what does it do? Stops. And once you know it stopped, right, you can use that electric field value to actually find how much charge is there. And that's how they discovered the charges in electron. Okay, we have that experiment. We'll do that later on. So yeah, charged particle of mass, this is provided here. The charged particle that you have here is in a field, plus 4,000 here. And this is minus 2,000, plus 2,000. This can confuse students. So what is the magnitude and polarity of the charge? So charge, how much is this charge? Find that for me, and also find the sign of the charge. That's the question. Okay, but before I start, is this going to give us a field, a plus 4,000 and a plus 2,000? Yes. Why? Because what's there between this? Potential difference. So it's not necessary it's a plus or a minus. What's necessary is there's a difference. Okay, so as long as you have a difference, it's a field, and it will work. And if the values are equal, field and nothing happens there. So yeah, there is actually a potential difference here. So the question for you is to find me the charge and its magnitude. Okay, so try Karo. One microgram is 1 million gram.
1 gram is 1 million.
Yeah. 10 to the power minus 6 micro. Oh, sorry, distance 5. Yeah. So a charged particle is held stationary, and you need to figure out how much charge does it have. Also, the polarity of the charge. When is it plus or minus?
Is it 4.905
Minus 13 plus.
plus 4.905?
Yeah. 3.924. Actually, wait. Possible actually. 3.924. Okay, I have to solve and check. That's also possible. Minus 13. Minus 19. No. I have the answer here. Charge. Something to the power minus 13. Minus 10. Acha, kore de, but why are you guys struggling? First of all, can you tell me if this thing is stable and balanced, right? It means that the downward force here, which is the what? Weight, must be equal to what? The upward force here. What is that upward force here? The electrostatic force. Now, can you tell me what charge should this particle have to be that it gets attracted upwards rather than downwards? Yeah, negative, right? So that's the first thing we need to get out of our way, that this should be a negative charge. Because if it was a positive charge, would it go towards the more positive or towards the less positive? If it's a positive charge, yeah, less positive, right? But I have to make sure my particle goes where here, upwards, right? And that can only happen if it's a negative charge. Now the question is, what is this force? So we have to write a statement here in equilibrium, because this is stable. In equilibrium, the upward force must be equal to what? Yeah, the downward force. Now the upward force is the electrostatic force, and the downward force is the what? Weight, because that's the downward force, right? So what's the formula for electrostatic force? F by Q equals to V by D. So F equals to what? VQ by D. No, Ajay. F by Q is equal to what? V by D. So what is FE going to be? Yeah, VQ by D. So it's VQ divided by D kola. And what is weight going to be here? Mg. That's it. Just solve this. So V is going to be what? The potential difference, 2000. What is the charge? That's what we need to find out. What is the distance separation between the plates? 5 centimeters. So that's 5 divided by 100. Equals to what's the mass of this particle? 2 micrograms. So 2 into 10 to the power minus 6. Into G is how much? 9.81. So yeah, if you solve this, Josh, that's the answer. 4.91 into 10 to the power minus 10. Oh, sorry, this one. What did we do? Oh, yeah, sorry. Thank you. So this should be divided by 1000 again. Yeah, in that case, what's the power going to be? 13. Right, so that's the answer. Follow confusion. Why is the charge negative? It is negatively charged. No, so one of them was. It is negatively charged since the Fe must act upwards. And the top plate is more positive. Yeah, so the object's weight is supposed to act downwards, right? So if the object's weight is acting downwards, it should go down. So to prevent it, you have an upward force. Done? Everyone? Okay, so we'll move on. এখন হচ্ছে page 98 এর পাশে যাও. This is the path of charges in an electric field that's perpendicular to the field. Okay, so এটা হচ্ছে uniform electric field. And projectiles. We'll see why projectiles. Right, so uniform electric field and projectiles. How is like a projectile chapter in our electric field topic, right? So let's see. All right, so look at this. You have two parallel plates, and one of them is positively charged, and you have another plate at the bottom that's negatively charged. And we found that as the particle is released, a charged particle is released in the field, what does it experience? A force, right? Can you tell me which way does the force always act? Always, without any exception. Yeah, positive to negative, and it's always parallel to the direction of the field line, right? And perpendicular to the plate, which what I'm trying to say here is the force is always going to be downwards. So if your particle is going this way, which way is the force acting? Downwards. If your particle is going that way, which way is the force acting? Downwards. If your particle is going straight, which way is the force acting? Downwards, right? So that's what we're going to see right now. So if you have a charged particle enter the field like this, right, with a velocity v, and as it enters the field, immediately there's going to be something acting on it. What? A force, right? Which way is the force going to act on the particle as it enters the field? Right, vertically downwards. Does this remind you of anything? Yeah, so projectiles, right? Projectiles key hoy gravitational field er moddhe, if you throw a ball, right, horizontally, you're giving it a horizontal velocity, but what's acting downwards on it? Weight. And what does the weight remain throughout? Constant, right? Isn't it the same scenario here? So as a consequence of that, what will happen is your particle in this field will take a what path? A parabolic path. Yeah, that's something important. So this is a positively charged particle. Why? Because the force is acting downwards. And as it keeps moving through the field, can you remind me, how does V change? Yes, good. V will remain constant because we learned that there's no force acting horizontally here. So there's no horizontal variation. But can you tell me what happens to your vertical velocity? So initially there's no vertical velocity. Yeah, and it increases. And it increases at a what rate? Increase in rate, because you have acceleration here. And শেষে গিয়ে এটা এরকম দেখতে হয়ে যাবে. Remember all these? And that's the reason why the path looks what? Curved, right? So it's going more and more downwards. What if these two were same all the time? What kind of a path will you have? Yes, very good. A straight line. It'll be just like that. Okay. So anyways, this is your uniform electric field, and this is the path taken here. So আমাদেরকে এখন যেটা figure out করতে হবে, and I need your recommendations here, is how do particles behave in different scenarios? So for example, I will fire a particle here with velocity, this is mass m, by the way, okay, mass m, velocity v, 2v, and 3v. You need to tell me how would the paths look like for each of them. So I'll give you a reference. This is v. So if this is the path taken by v, what should the path be for 2v, 3v, and yeah, that's it. Like, how does the path change based on velocity? Right. So that the place where they go and hit is going to be the same. Why? Yes. So because of that, they'll go and hit the same place. Yeah. So all of them are vertically the same height, right? So you're saying they'll go and fall at the same place. Why?
Because velocity moves, so they will be shorter than they can do.
Okay, tell me something. Let me clarify this. Alarm in Java, I'm worried. So the time taken for this particle to fall here and the time taken for that particle to fall there, same, like different? Same. Why? Because what's bringing them down? Oh, in this case, the electric field, right? So the electric field is same for all of them. So they all take the same time to hit the bottom, right? But in the same time that they take to hit the bottom, there's a vertical velocity involved here. If the vertical velocity is higher, would they travel the same, if the horizontal velocity is higher, would they travel the same horizontal distance in the same time, or will they go further? Further, because there was a formula for this dedicated Ranger formula. What was it? Range equals to horizontal velocity into what? Time of flight. Do you remember this equation? So time of flight is what for all of them? Same. So if my horizontal velocity increases, what happens to range? What happens?
That's what we said.
No, I know, but I expected everyone to say the same thing, given that it's not even a year that we did this before. So anyways, the higher the velocity, the further they go, okay? So এখানে হচ্ছে এটা কি হবে? V, 2v. Yeah, mass different. I know you were thinking of that because the way you said same height হচ্ছে, but that's the mass, not velocity. Okay, so এখানে কি হচ্ছে? What is this criteria? Same mass, but different V. I'll give descriptions on this, okay? Don't worry, because it already জিজ্ঞেস করে কেন. Now let's move on to the next criteria. The next criteria is same V, different mass. Okay, so once again, we are firing particles into the chamber here, in the field here, and each of them will have the same velocity, V, but of what masses? Different masses, okay? So that. So এখানে হচ্ছে the path that I'm going to draw right now is the path for, let's say, M. You need to figure out what should the path be for 2M and 3M. Same. আচ্ছা, okay. একটু চিন্তা করে answer করো এবার, দেখো। Same. Achha, does everyone agree that if it's a 2M and a 3M, the mass increases, the path will still be the same? Yeah, the question is that you have this particle fired into the chamber here. This is velocity V, right? the mass m took this path. So if I have double the mass or triple the mass, right, how would the path compare? Shorter. মানে mass যদি বাড়ে তাহলে ওর কাছে এসে পড়বে। আচ্ছা, okay. Varying answers. Online আবার উল্টা. So let's take a poll. How many of you think that it'll just follow the same path? The exact same path. Yeah. I mean, you should take a hint. এতদিন পরে একই জিনিস করানোর কথা না আমার। আচ্ছা, but anyways, how many of you think that the heavier mass will fall closer? Heavier mass will fall closer. That's okay. And how many of you think that the heavier mass will go further? Oh, they have same charge. Q. Okay, let's cut to the chase. Everyone's wrong. Okay, because যেটা আমি লাস্টে জিজ্ঞেস করছি যে কেউ হাত উঠাও নাই। The correct answer is the heavier mass will go further and the lighter mass will fall closer. And the reason why you guys got this wrong is because, let me clarify, তোমরা যেটা ASA করে আসছো, you remember that the gravitational acceleration G was what always? Constant. So a heavy mass, a light mass, a big mass, a small mass, they all fell at what rate? 9.81. This is not gravitational field. It's electric field. And electric field এর মধ্যে mass change হলে acceleration change হয়। বলো। So কি হবে আমি বলি, দেখো। So what was it? F by Q equals to V by D, and that's MA by Q equals to V by D. So what's my acceleration going to be here? VQ divided by M into D. Do you see that mass now has an impact on your acceleration? Unlike gravitational field, the mass didn't have an impact. Whatever mass it was, what was the rate at it which fell? 9.81, right? So because mass is heavier, acceleration কি হবে? কম হবে. And if something accelerates slowly, will it fall more rapidly or will it go further, right? So এটার analogy টা বুঝাই. Let me clarify. There's actually a very nice analogy for it. So imagine this room is like a wind tunnel. You know what a wind tunnel is? There's like wind blowing here for testing purpose, right? I have a golf ball in my hand and I have a table tennis ball in my hand. What are the different masses? Same size and everything. And there's wind blowing this way, right? I take the golf ball, which is quite heavy, by the way, and I take the table tennis ball, which is very light, and I throw both of them, right? Do you think that both of them would curve the same way? No. Which one will curve rapidly? Table tennis ball will go like instantly that way, right? But the golf ball will curve slowly, right? Because they have what? Different masses, and because of different mass, they'll experience different what? Acceleration. So the one that accelerates very rapidly because of its low mass is which one? The table tennis ball. So there's another place you learned this, and then this was in your O levels. You remember that when there's a magnetic field and you send like an alpha particle, a beta particle, and a gamma radiation, the gamma went straight through, the alpha did like a curve, the beta did something strange. Yeah, it spiraled very rapidly. And what was the reason behind that? The beta is like 4,000 times lighter than the alpha. So that's why it spirals very rapidly. Okay, so yes, the bottom line here is that you have to now take into consideration what to get your answer. The fact that the acceleration changes. Okay, and I don't know if you have done this in chemistry. Those who have chemistry, have you done the mass spectrometer? Mass spectrometer মধ্যে হচ্ছে there's something called the mass to charge ratio. What is that?
The ratio of mass.
Why is it important? Where do you learn, like O levels? Yes, acha. So mass spectrometer কি করা হয় বলে, it's a device where you send different ions, right? And the different ions get deflected. There's a magnetic field and there's an electric field, right? So the different ions get deflected and they create like these lines that you can read. Have you heard of that? Acha. ওই lines গুলো separated হয়ে যায়. The ions get separated. What separates them? Their mass and charge ratio. So they have different mass, different charge, which splits them up. Now you can separate them and figure out what the sample is made up of, right? So again, our acceleration, if you look closely here, I'm going to redo this thing here. The acceleration here actually depends on two factors. What are the two factors here? I'm using the equation. Is V changing in my setup? No. Is D changing in my setup? No. So if I can consider this to be a constant, right? The acceleration that you have here is proportional to the ratio of what by what? Charge by mass. So now onwards, right, in an electric field, the mass and the charge both together will give you like the final effect. Okay. So here's the thing. What if I double my mass and I double my charge, how would the path change? Same. Because if I double my charge and double my mass, isn't the acceleration the same as before? So it just takes the same path. So you get my point, right? Now both of them have to be taken into consideration. Okay. So yeah, that is what you need to learn. Asha kori buchcho that from now onward you can apply the same rules of gravitational field anymore, because there's a factor that is not same anymore, which is acceleration can change. Right. So I'll give notes on this if you copy it. So let me see if there's an animation on this. Which one I don't know. All right, look at this. So you have this plate here. So if I fire a particle here, and I have a potential difference provided, I have magnetic field here. There magnetic field to magnetic field 0 G for it. Right. So this is the one that we did earlier. So do you see that there's a particle here? And what I'll do is I'll provide a voltage. And as I provide a voltage, do you see that the particle is going up like that? Why is the particle going up like that? Because which force is more here? Yeah, I'll rerun this. There's a Charapore, it's going upwards, right? Because the upward force is higher, right? Can you tell me what can I do here to make the particle move downwards? Yeah, so I can increase the mass or decrease the voltage. So if the voltage is 0, which way the particle go? Is down, because there's nothing to balance it, right? So what I'm going to do right now is slowly increase this, and I'll try to make it equal. In that case, you'll find that it is still pore jaচ্ছে, which means what is it? I haven't made it equal yet, right? So your Millikan was basically doing this. Remember, I told you that they have to tweak the value around, and you have to tweak the value around until the two values become what? Equal. And if they become equal, what do the particle do? Yeah, stationary. And that's what Millikan did. He found the value at which they became stationary, and F by Q, V by D, F ta jane, because weight. V is what? The potential difference. D is what? The separation of the plates. Using that, what did he find? Q. And the Q that he found was the charge of the electron. This was done, 200 years back, but the value was very accurate. We know that the electron charge is 1.6 into 10 to the power minus 19, right? Millikan found it as 1.59 into 10 to the power minus 19, which is like really precise for its time, right? And he did it using this setup. It's called the Millikan oil drop experiment. He did it in a vacuum so that the air doesn't cause any interference. Okay. Acha, এটা হচ্ছে the one that I just showed. So what does it do here? It bends upwards, right? Now let's tweak around and see কি করা যায়. So আমরা হচ্ছে velocity বাড়াবো. You see নিচে একটা slider আছে velocity জন্য. So if I make my velocity higher, what do you think will happen now? Yeah, so it'll go further and hit the plate there. Okay, let's try something else. Let's increase the charge of this particle. What do you think will happen? It, I mean, জিজ্ঞেস করি না last time. So can you tell me what will happen if I increase the charge of the particle? Okay, we'll start with something here. Our charge হচ্ছে -1, let's say. See what it does. নিচে চলে গেল. Okay, it's all fine because the bottom plate is positive, right? What if I make my charge -5? Do you think it'll go and hit the same place? Will it go further or will it come closer? Let's see. Yes, and why is that so? High charge means high force. High force means greater acceleration. Greater acceleration means it falls faster. Okay. Our mass যদি বাড়াই দেই, what do you think is going to happen right now? Will it fall at the same place or will it go further or closer? So see, it goes much further. Cannot, because it's now heavy, right? So acceleration is what? Yeah, the acceleration is now less, so it takes longer to go and hit the floor. Okay. Yeah, so in the like if they ask you for a reason for it, yes, you have to use that A equals to Q by M and explain using that. Acha, so I'm যেটা করবো এখন হচ্ছে I'll upload this today to copy করে নিও. So these are all the definitions and explanations that I've provided. Okay, so I'll just add them there. তোমরা পড়ে দেখতে পারো এখন. If you have any question, you can let me know. But the main idea is that mass does have a factor. Okay, it's no more independent. Wednesday. Acha, those who capacitors, right? Wednesday the barba, like after the class 5 onwards. Okay. So this Wednesday I'll take a class on capacitors. যদি কারো লাগে, anyone else করতে পারো. Yeah. I'll first give you like a basic explanation of the whole thing. It's a very small chapter, and then if you have any questions, you can shoot. Also, if you have questions from other chapters, bring them.